Okay, so for the first one here, we have 4.5 bushels equals blank gallons. Now I purposely chose these because hopefully they're units that you haven't had a lot of experience with. So maybe your comfort of just jumping in and multiplying or dividing isn't there. So 4.5 bushels. To do that conversion, we make it into a fraction. It's 4.5 bushels over 1. And then we're going to use that conversion factor. That conversion factor, remember, is equivalency. That's what I gave you right here. 1 bushel equals 8 gallons. And we're getting rid of bushels, so we have to cancel that out mathematically. Since bushels are on top in our fraction, or in our original measurement, we put them on bottom in our conversion factor so that they will cross cancel out. Then our equivalency is 1 bushel equals 8 gallons. And now we should double check. We are canceling out bushels. The bushels are gone, and we're ending up with gallons, and that is where we want to be. So we can go ahead and do this calculation. 4.5 times 8 is 36. It is times gallons, so it's gallons be the unit there. And on bottom, it's 1 times 1 with no unit. So 36 gallons over 1 is just 36 gallons. Over here on the second one, similar type of issue. We have the 77 yards, but we're not real comfortable going into rods. It's not a unit we use all the time. So we'll set it up again with a conversion factor. Put the 77 yards over 1. Excuse me. And now we're going to convert. So in our conversion factor, we're getting rid of yards. So we're going to put yards on bottom. We look at our equivalency. 5.5 yards is equal to 1 rod. So again, we double check. The yards cancel out. Yards cancel out, and we're going to be left with rods, which is what we want. So now we go ahead and we multiply 77 times 1 rod is 77 rods over 1 times 5.5 is just 5.5. So we do have to divide that out. 77 divided by 5.5 is going to give us, what was that, 14, I believe? So 14 rods. Now, what we did there is an example of dimensional analysis. And dimensional analysis is an extremely powerful tool in the math and especially in the sciences, because it allows us to do calculations even when we don't necessarily know what the formula is. We know what we're starting with and where we want to go with it, and we allow the dimensions to determine the calculation from there. For example, here we started with bushels and we wanted to go to gallons. Well, we let the dimensions tell us where to put things in this conversion factor, and then the operations just followed from that. An example of dimensional analysis might be dealing with speed. Let's say that you are traveling 420 miles at a rate of 60 miles per hour. Now, to make this work, rates are actually an equivalency. 60 miles per hour can be thought of as 60 miles is equivalent to 1 hour of travel. And when you look at it like that, that equivalency now can become a conversion factor. If our question being asked here now is how long is it going to take, we can take our given information, the 420 miles. And of course, most of us know the formulas for working with speed and travel distance and all that. But if we didn't know those formulas, the units will guide us. So we start out with our given information of 420 miles. We put it over 1, and we can now use this conversion factor, 60 miles equals 1 hour, to convert that. So we're going to put miles. We have miles on top. We're getting rid of those, so we're going to put miles on bottom. And we have this rate gives us an equivalency of 1 hour equals 60 miles. So here, the miles do cross cancel out like they would in any fraction. 420 times 1 hour is 420 hours. And on bottom, we have 1 times 60 is 60. We divide that out. 420 hours divided by 60 is 7 hours. So you can see the units totally determine how we had to do that calculation. Even though we may not have been totally familiar with the formulas, or we couldn't remember the formulas at the time, the units guided us through. That is the correct answer, and that's what we would have got from the formulas. We just didn't have to memorize the formulas. As we get into Unit 3 starting in next week, we are going to do a lot of different dosage calculations, and there are a ton of formulas you could memorize to do those calculations. But if you understand how to do dimensional analysis, you don't have to memorize any of them. The dimensions tell you how to do those calculations. So that's kind of where we left off, and we're going to look at that dimensional analysis a little bit more later on. This textbook gets kind of crazy with the dimensional analysis, but we'll take a look at it. It's just good practice in working with variables and units and stuff like that. So anyway, we left off, we had talked about all of our standard units of measure on Friday. So today we're going to take a look at our metric units of measure. A few notes about the metric system. The metric system was developed in the late 1800s, so it has been around for about 130 or 140 years now. One of the advantages of the metric system is it is a created system. Now, by created, I should have added in there intelligently created. Not that our standard measuring system wasn't very intelligent. It was very clever for the time when there was no current measuring. But in our standard system, remember we said on Friday that it was what we called an evolved system. It started out to fill a need, and it filled that need. In fact, there are several different needs that were filled through time, and it evolved. The needs evolved, so they changed the system and adjusted the system until they ended up with this big conglomerate of getting it all squeezed together that was kind of a mess. But that was because it wasn't ever planned to be used together. They filled specific needs as they popped up and adjusted. And that's why we have things like 12 inches in a foot and 3 feet in a yard, or 16 ounces in a pound and 2,000 pounds in a ton. Because those units were never intended to be used together. They each individually were developed to fill a need, and later they were adjusted and put together to make a measuring system. And that's why it's so awkward. So in the metric system, when they went to develop it, they had been using measurement for a long time, literally thousands of years. And so they knew the strengths and weaknesses of that existing standard measuring system. So they were able to build on the strengths and attempt to eliminate the weaknesses. And so let's look at some of the things they did to do that. The first thing they did was they wanted to eliminate multiple units for every type of measure. You know, in the standard system, and I'm going to kind of compare the standard system to the metric system a little bit here. I'll put metric on the left side here. And we put our standard on the right. For length, in the standard system, we had the inch, foot, yard, rod, mile. To fill in some of the other ones, we had the hand, the cubit, furlong, fathom. All of those different units, and there are more of them, there's a chain. All of those different units were developed to fit a specific need, and they fit that need, and later they were adjusted so that we could convert from one unit to another and put together to make a system. But it's way more units that we ever need. In fact, many of those units disappeared. The fathom, the cubit, the hand is still sort of used, but many of them disappeared completely, and a lot of others were faded into the background, only used for very specialized applications. So in the metric system, there is only one unit of length, and that is the meter, sometimes spelled M-E-T-R-E, the European spelling of meter. The same for capacity. Remember, there's a difference between the volume and capacity. Volume is a length unit measured in 3 dimensions or cubed. Capacity, in our standard units, that would have been the gallon. Now, the quart actually was developed from the gallon, so that wasn't its own unit, really. The pint, the cup, tablespoon, teaspoon, bushel, peck, a barrel, even the pinch, dash. There's all sorts of units of capacity that have been used. There's hogshead and several others out there that many of us have only heard as far as references to the slang and old sayings and stuff like that. So for capacity, they have only one unit in the metric system, the liter. Again, European spelling is TRE instead of TER. Now, the other big weakness was there was no direct conversion between volume and capacity in the standard system, because that gallon really just came from a hat size. It wasn't really thought out to be, cubic inches or cubic feet or anything like that. We had that 1 cubic foot was like 7.48 gallons, just under 7.5 gallons. Or 1 gallon is approximately 231 cubic inches. Very ugly conversions from capacity to volume. In the metric system, they knew about this weakness in the standard system, so they tried to correct it. 1 liter is equal to 1,000 cubic centimeters. Now we'll talk about what centimeters are later on, what that prefix is. Or 1 milliliter is equal to 1 cubic centimeter. And this conversion here is actually very important in the medical field. It's a 1-to-1 ratio. They designed a milliliter to be a cubic centimeter. They came up with how they wanted the system to be set up first. Then they developed the sizes so that these things matched up. Now we said mass was a big, let's talk about weight first. Remember, weight is the force of gravity, and that's what we use mostly in our standard system. That's where the pounds, ounces, tons, drams for apothecary units, minims, grains we talked about. There's drops that have been absorbed in the metric system and so on. A lot of different units for weight. In the metric system, they tend not to focus on weight. The standard system focuses on weight. We have all these different units for it. In the metric system, the focus is not on weight. There is a unit of force or weight, and that is the Newton, which unless you get in deep into the sciences, you probably won't see that a whole lot. Chemistry or physics, you'll see that come up quite a bit. In the metric system, they tend to focus on mass. Now, in the standard system, there was just the 1 unit of mass that we brought up, which was the slug. Mass was not really developed as a concept until later on in history, so it didn't get as many standard units developed for it. In the metric system, the only unit of mass is a gram. Now again, the gram was intelligently designed to fit in with the other units. The gram is defined to be the mass of 1 milliliter of water. So again, there's that direct conversion from capacity to mass. So there's ways we can convert. In the standard system, it comes out to be like should be 128 fluid ounces to 1 gallon. I mean, it gets to be really ugly conversions there. So they worked out, not only did they eliminate all these multiple units, they got it down to just a single unit for each type of measurement in the metric system. They made it so converting from one type of unit to another was fairly simple. From length to capacity or volume to capacity was very simple. And then given a standard substance like water, from volume, capacity to mass. So let's look at the metric prefixes. And this chart is actually very, very powerful in the metric system. We have our main units for each type of measurement. We have the meter, liter, and gram. And of course, there are other types of measurement that we haven't mentioned here that do have metric units. There's land measurement for the R and stuff like that as well. But we're going to stick with those three for now. As we go into smaller units, we need to measure things that are smaller than a meter or a liter or a gram. Each of those, let's say that is 1 meter, 1 liter, 1 gram. We need to measure something smaller. There's the prefix deci. Deci means 1/10. So dm would be the abbreviation for decimeter. dl would be the abbreviation for deciliter. dg would be the abbreviation for decigram. Those would be 1/10 of a meter or 1/10 of a liter or 1/10 of a gram. Little side note here quick. The abbreviation for liter is just L. When I was taught the metric system back in the late 80s, I was always told that you had to abbreviate liter with a capital L. Well, the reason for that was to avoid confusion. If I have something like that, is that 51 or is that 5 liters? Well, if it's a capital L, it's very, very clear that that is 5 liters instead of 51. So it is okay, it is now acceptable to use a small L to abbreviate liters, but you have to make sure that it is very clear that that's an L and not a 1. Smaller than deci is centi. Centi is 1/100th. So a centimeter is 100th of a meter. Centiliter is 100th of a liter. Centigram is 100th of a gram. Next is milli. We talked about mil actually on Friday, where mil was 1,000. The mil rate is 1,000, or a mile comes from mil, 1,000 paces of a soldier in formation. Milli is 1/1000th. So mm is millimeter, 1,000th of a meter. ml is a milliliter, 1,000th of a liter. And mg is 1,000th of a gram. Now you can see here we went every 10. This was 1/10th, 1/100th, 1/1000th. They didn't go 1/10,000th and 100,000th. They skipped those. The 10,000th and 100,000th they didn't name. They decided that they had enough units in between there. So they skipped from 1,000th to 1/1,000,000th. And 1/1,000,000th is micro. Now, the abbreviation for micro, the official abbreviation, scientific abbreviation, is the Greek letter mu. Looks like that. Kind of like a U with a long front tail, or a P that doesn't quite close on top, however you want to look at it. In the medical fields, in medicine was one of the first fields that had to keyboard all their information into computer systems. Well, there is no mu key on the keyboard. So rather than having to go through a symbol menu every time they needed to keyboard that in the medical fields, they started to use MC as the abbreviation for micro. So for micrometer, which is a millionth of a meter, it was either mu m or mcm for micrometer. For microliter, you'd have mu L or MCL for microliter. And same for microgram, mu G or MCG. In medicine, you're going to see this last version more often than not. Our textbook, I believe, uses the mu just because it's viewing it from more of a scientific standpoint. And there are units smaller than micro. We skip from a millionth to a billionth, which is nano. About 10 years ago, you heard a lot about nanotechnology. It was kind of a hot topic. Nanoscience, nanotechnology. All that was the science of things that were really small. A nanometer, a millionth of a meter is what, or a billionth, sorry, of a meter is what a nanometer is. A billionth of a meter is about the size of a single atom. So when you're talking about nanotechnology, all you're really talking about is the science of things that are really, really small. Science of things that are about the size of a single atom. Now going the other way, if we had to measure bigger things, larger things, we had deca. The prefix deca meant 10. Now, dm was already the abbreviation for decameter, so DAM, or for decimeter, so DAM was decameter. DAL would be decaliter. DAG would be decagram. Those are 10 liters, 10 meters, 10 grams. We had hecto, means 100. So hectometer or hectoliter or hectogram were 100 of those. And then the one that you've probably all heard of, kilo, is 1,000. Kilometer is, what would, I don't want to say equivalent, but on the scale of our mile, it's actually quite a bit smaller, but how longer distance are measured. The kiloliter is 1,000 liters. The kilogram is probably more popular than the gram in medicine for measurement of people, of course. Obviously, it's not a weight, but that's the metric. They stress the excuse me, the mass. So instead of measuring weight in pounds, they measure mass in kilograms. And then just like on the other end, they skip the 10,000 and 100,000, and they jump up to 1 million, which is mega. Now you notice I spelled mega with a capital M because that's how they abbreviate it. Capital M, little m is a megameter. Capital ML is a megaliter. Capital MG is a megagram. Now, before we start talking about conversions, I want to make a few notes here. First of all, the megagram is 1,000,000 grams or 1,000 kilograms. Because a kilogram is a little bit more than 2 pounds, we'll actually talk about that direct relationship in a little bit. 1,000 kilograms is a little bit more than our 1 ton of 2,000 pounds. So the 1,000 kilograms has been come to be known as 1 metric ton. So instead of calling it a megagram, they usually refer to it as a metric ton. Also, you may have noticed that in here there are a lot of units that you're not terribly used to. And there's a good reason for that. They just don't get used. In most cases, we tend to use the main unit. We tend to use milli, kilo, and then, of course, mega for some really big things, not very often even, and micro for some really small things. The other units in between there, like hecto and deca and deci and centi, don't tend to get used very much. And it's just basically because the thousands were easy to convert, and it's not so hard to have 700 millimeters. You don't need to jump to 70 centimeters or whatever. Now in the US, because we tend to latch on to those standard units, the centimeter has become very popular, and mainly because it's the closest thing to an inch in the metric system. So we kind of latched onto the centimeter as one of our measures of length rather than the millimeter. If you go to Europe, they do tend to use the millimeter way more than the centimeter for things that we would normally measure in inches. Now, I'm not saying that those units are not applicable. Measuring land area, hecto does get used as a prefix quite often. That's about the only application I've ever seen the hecto prefix used in. Centi, as we said, for centimeters gets used. Deciliters get used a lot in medicine. All of our blood tests, if you go have your cholesterol checked and it comes back as a 145, what that is 145 milligrams of cholesterol, triglycerides, whatever they're checking, 145 milligrams per deciliter of blood. So let's look at doing some conversions within the metric system. Now, in the metric system, we could still use that dimensional analysis that we talked about above. If I wanted, but we tend to run everything through that main unit. So for example, if I want to convert 750 milliliters to centimeters, to use that dimensional analysis, I would set it up as a fraction. 750 milliliters over 1. And now over here, I'm going to put milliliters on bottom because I want to get rid of milliliters, centimeters on top. And I'm going to relate each of them back to the meter. A centimeter is 1/100th of a meter. A milliliter, centiliter, I screwed that up. Let me try that again. This should be 750 millimeters going into centimeters. Can't cross units here. So our 750 millimeters over 1. We got millimeters on bottom, so they'll cancel out going into centimeters. Centimeter is 1/100th of a full meter, and a millimeter is 1/1000th of a full meter. So now the millimeters cancel out. We have 750 times 1/100th is 7.5 centimeters over 1/1000th. Oops, I screwed that up. Got to be careful here. We got to equal. It's been one of those days. Let me step back and try that again. We'll start that all over since I got myself crossed up from the beginning. We have 750 millimeters. We'll put that over 1. And yes, we are getting rid of millimeters and going to centimeters. So our millimeters will cancel out. We need some equivalency between centimeters and millimeters. And we are going to go back in terms of that main unit. If we look up here, the main unit is going to be just the meter. 1 meter is equal to 100 centimeters, or 1 meter is equal to 1,000 millimeters. So in our conversion factor here, 100 centimeters is equivalent to 1,000 millimeters because they're both equal to 1 meter. Now we can go ahead and do our calculation. So we have 750. Oh, these pens going nuts. Me too now. So we've got our 750 times 100. That's going to be 75,000 digits. There we go. 75,000 centimeters. And on bottom, 1 times 1,000 is just 1,000. And that divides out, 75,000 divided by 1,000 is just 75 centimeters. So 750 millimeters is equal to 75 centimeters. Now, the reason I screwed up that process is because I don't do dimensional analysis with the metric system very often. It can be done, and there are going to be some processes you'll see that maybe the dimensional analysis might be a simpler way to go. But for simple conversions like this, the metric system was designed to be powers of 10. And if we recall, when we did our place values in our scientific notation, our place values are all powers of 10. So to get from one unit to a next, it's all about just moving place values. We are going here from millimeters to centimeters. On our chart, here is millimeters, here is centimeters. We are moving from millimeters to centimeters, which is one spot to the left. Each place on this chart is a power of 10 or one place value. The units moved one spot to the left. The decimal point can also just move one spot to the left. So from there, it moves one spot to the left to make that 75. And in any of our units, it can move that way. We might have 0.23 kilograms converted into grams. If we look at our chart, here's kilograms and here's grams. We are moving from kilograms to grams, which is 1, 2, 3 places to the right on our chart. We take our decimal point, move 1, 2, 3 places to the right. 0.23 kilograms is 230 grams. Now, that movement like that is a very simple way to deal with things when we're dealing in just the metric system. If we're mixing metric units with other units, it sometimes isn't quite that simple, especially if we are converting from standard into metric. You know, we have little equivalencies from standard to metric. And of course, back again. We're talking about length. You know, 1 inch is equal to 2.54 centimeters. If, for example, my height, I am 74 inches tall. If I want that in centimeters, we're going to have to go back to that dimensional analysis again. Put the 74 inches over 1. We're going to put inches on bottom so they cancel out and go to centimeters. 1 inch equals 2.54 centimeters. And we cancel out. The inches cancel. On bottom, we just have 1 times 1 is 1. On top, we have 74 times 2.54 centimeters, which is going to give us 187.96 centimeters. So divided by 1, that is just 187.96 centimeters. For capacity, we have that 1 gallon is equal to 3.785 liters. So if you're looking at filling the gas tank on your car, if you have a 16-gallon tank and you want to convert that to liters, put it over 1. And our conversion factor here, gallons will go on bottom, liters on top. And again, 1 gallon, 3.785. Gallons cross cancel out. We have 16 times 3.785. So we get 60.56 liters over 1. So your 16-gallon gas tank is going to hold 60.56 liters. Or for weight, we have 1, well, actually goes the other direction, 2.2 pounds is equal to 1 kilogram. So if, let's say that you weigh 180 pounds, and you want to convert yourself into metric. Now you'll notice I made a big deal about pounds being weight and kilograms being mass. So it is a very sloppy conversion. We're changing actually even the type of measurement, not just the units. But you know, as we had mentioned, because gravity is relatively constant on Earth, we tend to get sloppy between weight and mass. So we're going to ignore the fact that those are different types of measurement and make the conversion anyway. So on bottom here, we're going to put pounds going into kilograms. 1 kilogram is 2.2 pounds. The kilograms cancel, or sorry, the pounds cancel. 180 times 1 kilogram is 180 kilograms. Now on bottom we have 2.2. So now this one does have to divide out. 180 divided by 2.2. We get 81.82 kilograms. Now, that dimensional analysis here for making these conversions between units makes it a lot easier than trying to remember what we're doing. Now, you should always double check your answer, by the way. If the units get bigger, just like the scientific notation, if the unit gets bigger, the number has to get smaller. Well, a kilogram is bigger than a pound, so the number here better be smaller. 81.82 is smaller than 180. Same up here. A gallon is bigger than a liter, so when it went from gallons to liters, the unit got smaller. The number better get bigger, and it did. That dimensional analysis can help us convert when we get into some other units as well. Like, let's say that we have, well, let's say you're in Europe and you see a gas station, petroleum station, whatever you want to call it over there, that has fuel priced, and we're just going to say that it's in American dollars, for $1.40 per liter. You want to know what is that equivalent to what we're paying here compared to what we're paying here. Well, that $1.40 per liter is our starting point. And remember, we said those rates like that can be written instead of just $1.40 per liter, we can write it as $1.40 per 1 liter. And now we can use a conversion factor. We want to get rid of liters and convert that to gallons. Now, in this case, liters are on bottom, so we're going to put them on top so they cancel out. Gallons will go down on bottom. So 1 gallon is 3.785 liters. And now the liters cancel out, and we just multiply. On bottom, we have 1 times 1 gallon, which is just 1 gallon. On top, we have $1.40 times 3.785, which is $5.30 if we round to the nearest penny. So that's $5.30 over a gallon, or $5.30 per gallon. So you can see the dimensional analysis helped us figure out how to do that calculation by just simply placing the units in the right place so that they will cancel out. So I've been stressing that dimensional analysis. Let's take our last few minutes to talk about that a little bit. On the practical side, we're going to see dimensional analysis used a lot in converting our measurement conversions and our dosage calculations. But there is a section in your textbook that hits on that, and it takes it to a little bit of an extreme. And it even talks about, like, if we have something to the power of -1, like m to the power of -1, just think of it as a variable. Remember, that is equivalent to 1 over m. So m to the power of -1 times m, what that's really saying is 1 over m times m. And if you use our rules of fractions, 1 over m times m can be thought of as 1 over m times m over 1. And it's a mouthful. Multiply it out, you've got 1 times m is m times 1 is m over m equals 1. So m to the -1 times m is just 1. So if we use some of our metric units, a gram to the -1 times a gram is just 1. Or a liter times a liter to the -1 is just 1. Or centimeter to the -1 times a centimeter, again, just 1. The other thing is we might have, as we saw here, 1 over a centimeter times a centimeter can cancel out. We put the centimeter over 1, and we could either cross cancel the centimeters or we can multiply it out and reduce. It's also going to be equal to 1. So we can cross cancel within those fractions with those units as well. So we might get something as extreme as this. A meter times a gram squared over liter to the -1 times meter to the -1 That's all times liter negative 1 over meters squared gram. Now, looking at this, that looks to be really ugly, and it is. I won't deny that. First thing we see, we can cross cancel the liter to the negative 1. Those are both the same unit. We can cross cancel. Now, don't ask me what a liter to the negative 1 is. It's kind of a nonsense unit, but in this book, it takes it kind of to the extreme to practice the dimensional analysis. On the other side of it, we have grams squared and grams. So I'm going to write grams squared as grams times grams, because that's what squared means. And I'm going to cross cancel a gram and a gram. We also have meters squared here, which is meters times meters. So I can cross cancel a meter with a meter. And now we multiply straight across. On top here, I have grams times, there's nothing there, so that's just grams. On bottom, meters negative 1, that's gone. Meters negative 1 times meters cancels out, that's just 1. So it's grams over 1, or just grams. Now, like I said, some of these units here are kind of nonsense units. We don't use a liter to the negative 1, has no physical meaning. But when you get into science, chemistry, and stuff like that, there are things out there that are physical constants that have units like that because they need to have those units to make the math work out in the dimensional analysis. Okay, we are almost out of time here. Last time on Friday, if you recall, I assigned page 103, 1 through 19, the odds, which started the measurement conversions. And we're going to have to continue today on to page 110, 1 through 41, the odds. And then also page 114, 1 through 25, the odds. So this is the bottom one here, the page 114 is your dimensional analysis. You don't have to get overloaded with those, but do a few because that gets to be a lot kind of confusing to a lot of students. Were there questions out there? No? Okay. I am a little bit behind on posting videos. Friday's video is not posted on Blackboard yet, so I will have that up. If not by the end of the day today, I'll have it up early tomorrow morning along with today's video. We've had some network issues, so when I've gone to do it, our network's been down, so I'll get caught up here shortly with those. Otherwise, you guys have a great day, and we'll see you on Wednesday. And remember, test is Friday.